Theivanai Ammal College for Women. Learn, live and lead.
Myself, Yarthana, Assistant Professor, Department of Physics in Theivanai College for Women, Villupuram. Today I am going to explain Bohr atom model. Actually, Bohr, he has explained and he has followed the Rutherford atom model. He just overcome the defects of the Rutherford atom model. He proposed two postulates. The first one, an electron cannot revolve around all those orbits. It can only revolve around the permissible orbits. That is the first postulate. An electron can revolve around the permissible orbits for which an angular momentum, it is an integral multiple h cross. Okay, and the second postulate is an electron an electron radiates the energy when the electron jumps from the higher energy state to lower energy state. When it emits the energy, the emission of energy is h nu, and we can also call it as a photon. Okay, and I'm going to explain the briefly of first postulate. See here, an electron can revolve around the permissible orbits. And it is which is equal to integral multiple of h cross. See here, the integral multiple, it is represented as h cross. Where it is belongs to the h cross is h divided by 2 pi. H is nothing but it is the Planck constant, and 2 pi, we know here the electrons revolve around the circular path. So from the circular, we can define the circumference of the circular. So circumference of the circular is 2 pi. So h divided by 2 pi, which is equal to the h cross. The value of h is 6.654 into 10 to the power minus 34 joules second, and we can apply this value in this equation, and h divided by 2 pi. So 6.654 into 10 to the power minus 34 joules second divided by 2. We know the value of pi, 3.14. So finally we'll get 1.0545 into 10 to the power minus 34 joule second. This is the integral multiple h cross. Okay, now we have to find the electrons revolve around the nucleus, and when electron is revolve around this orbits, it doesn't radiate any energy, and one more thing, it is also stationary. Okay, and now secondly, the electron having a mass m and it's moving with some speed, that is represented as v, and it's having some radius. So radius is r, for which an angular momentum is mvr. Okay, an electron having the angular momentum, so the angular momentum of electron is r omega. So we can replace this value in above equation. So L, which is equal to m r square omega, which is equal to n h cross. Actually, angular momentum, which is equal to integral multiple h cross. I already said this thing. So m r squared omega, which is equal to n h cross. Why I keep here n? This is not happening the single time, it is happening the number of times. So I have written n h cross. N is nothing but the principal quantum number. So the value of n is 1, 2, 3, etc. Okay. This is the explanation for the first postulate. And second postulate is an energy is radiate when the electrons jumps from the higher energy state to lower energy state, or initial energy to final energy. See here, this is the higher energy state and this is the lower energy state. The electrons comes from higher energy state to lower energy state when it is radiates some energy. That energy is h nu. Okay, so that is the thing is h nu is ei minus ef. EI and EF is nothing but higher energy state or lower energy state. It's similar to the initial energy and final energy. Okay, from this we can write EI minus EF divided by H. And EI is the initial energy, F is the final energy, H we already know the Planck constant. And one more thing, the energy it's like a waveform, it's a radius, some energy is the waveform. That wave, from that wave we can find the frequency nu which is equal to EI minus EF divided by H. Okay. Okay. From these two postulates, we can define the formulas. What are the formula is? First one is the radii of the stationary orbits. And second point, the total energy of the electron in the orbit. Okay, so now I'm going to explain the radii of the stationary orbits. Consider an atom. This atom having a nucleus, the nucleus it is always having the positive charge. This thing we know, and it having some mass, that nucleus having the mass, we should represent the mass in m. Okay. So for hydrogen, I'm going to explain the radii of stationary. So for that I'm going to take one simple example. So for that I'm going to take the hydrogen atom. So hydrogen atom Z which is equal to 1. For the hydrogen atom, the electron having the negative charge, we know electron having the negative charge, so I kept the symbol here, and it's revolving around the nucleus. So the radius of the orbit is r. Okay, so the electron mass it's represent small letter m. See here, the nucleus mass should always be greater than the mass of electron. See how I represent here m. But for this calculation we are not considering the nucleus of the mass, we just only considering the mass of the electron. So the electrostatic force of attraction between the nucleus and electron, the value is 1 by 4 pi epsilon naught Z, which is the nucleus, and electron divided by radius, because the electrons is revolving around the nucleus with radius. Okay, so the value is 1 by 4 pi epsilon naught ZE, and for this electron minus E divided by the radius is represented as r square. Okay, okay. See, one more thing is here, the electron is revolving around the nucleus in the circular path. The electron is depending on the nucleus. So here the centripetal force also existing. The centrifugal force value is, the centrifugal force is mv square divided by r. And one more thing I said, the system is, it should be a stable. So the system, it should be stable means the electrostatic force of attraction between the nucleus and electron, which is equal to the centripetal force. So we can write here stable mv square by r, which is equal to Ze square divided by 4 pi epsilon naught r square. So from this equation we can find the speed v square. For that I am going to take, according to first postulate, we know the value of angular momentum. What is the angular momentum? mvr, which is equal to nh cross. Here also v is present and we need value of v. So I just keep here v and remaining terms will be going the right hand side. So mr, and I am going to square this term. So n square h cross square m square r square. Finally, we will get the value of v square, n square h square, cross square divided by m square r square. Now, I am going to substitute this value of v square in this equation. See here, m value of v square, n square h cross square divided by m square r square, which is equal to Ze square by 4 pi epsilon naught r square. Okay. See, our ultimate aim is we should find the radii of the stationary orbits. Okay. Here r is there. So we need only the term of r. So I'm just keep here r and I'm going to take a remaining term to the right hand side. So 1 by r is at e square by 4 pi epsilon naught r square. Remaining term n square h cross square by m square r square, and on m is here, so it's come to here. Okay. And I'm going to take this term to upper and Z e square m square r square by m 4 pi epsilon naught r square n square h cross square. See here also r square is there and here also r square is there and m is there. So I'm going to cancel this term. So finally we'll get Z e square m m by 4 pi epsilon naught r 4 pi epsilon naught n square h cross square. Okay, this is the value of 1 by r, but we need the term of r. From this term, see here, r, which is equal to 4 pi epsilon naught n square h cross square divided by Z e square m. Okay, I'm just change this term 4 pi epsilon naught n square h cross square, and this term it be a upper side and Z e square m, it's going to denominator. Okay. Okay, r, which is equal to 4 pi epsilon naught n square h cross square divided by Z e square m. This is the radii of the stationary orbits. And one more thing I have said, the system, it is not a particular time, it is happening many times. So I'm going to write this term in Rn 4 pi epsilon naught n square h cross square by Z e square m. Okay, this is the radii of the nth permissible orbits, which is equal to Rn, which is equal to 4 pi epsilon naught n square h cross square by Z e square m. Okay, this is the first formula. See, according to Bohr atom model, Bohr, he has introduced one radius. Bohr radius the Bohr radius value is A naught. So A naught, which is equal to 4 pi epsilon naught h cross square by Z E square em. So we can change the value of Rn. So A naught n square. This is the radio of the stationary orbits. Okay. And the second term, the total energy of the electron in the orbits. The total energy of the electron in the orbits. The total energy of the electron, how we can calculate means, the total energy of the electron, it's sum of the potential energy plus kinetic energy. Here, the potential energy, it should be a 0. Why I am telling it should be a 0? It is kept infinite distance from the nucleus. See here, suppose you just assume this thing. Here nucleus, many shells are there or orbits are there. Suppose the energy, potential energy, it is keep here and nucleus it's here, the distance is more. So the value of potential energy, it should be a 0. Okay. Okay. But the potential energy of the value or its work done is obtained. How it is obtained means by integrating the electrostatic force of attraction between the nucleus and atom, we can get the potential energy value by limiting infinity to R. So the potential energy of an electron is infinity to R Z E square divided by 4 pi epsilon naught R into dr. Okay. So now I am going to integrating this term. So Z E squared by 4 pi epsilon naught R infinity to R. Finally, you will get, I already told you, it is an infinity distance. So the value of potential energy, it should be a 0. So the first term, it should be 0. See here, Z E squared divided by 4 pi epsilon naught R, infinity minus Z E squared by 4 pi epsilon naught R. Okay. So this term, it should be a 0. So finally we'll get minus Z E square by 4 pi epsilon naught R. This is the value of potential energy. The next we have to find the kinetic energy. Okay. What is the kinetic energy? We know the formula of kinetic energy, but here the kinetic energy of an electron is of mv squared, and the system, I said the system, it should be a stable. From that we can write the mv squared. See here, mv squared by r, which is equal to Ze squared by 4 pi epsilon naught r squared. See, this is nothing but the centripetal force, which is equal to the electrostatic force of attraction between the nucleus and atom. Okay, so now we have to cancel this term. So mv squared, which is equal to Ze squared by 4 pi epsilon naught r. Okay. See here, the kinetic energy of an electron value is half mv squared. Here also mv squared. We know the value of mv squared. So we can replace the value of mv squared. So of Ze squared by 4 pi epsilon naught r. Okay. Now we can multiply this term. So Ze squared by 8 pi epsilon naught r. Finally, we can calculate the total energy. So total energy, which is equal to what? Potential energy plus kinetic energy. Okay. So I am representing the total energy En, which is equal to Ze squared by 8 pi epsilon naught minus 4 pi epsilon naught. This is the value of potential energy plus Ze squared by 8 pi epsilon naught r. This is the kinetic energy. Okay. Finally, we'll get, we have to cross multiply this term, and finally we'll get Ze squared by 8 pi epsilon naught r. Okay, this is the total energy. And one more thing, here we can already found the r value. Okay, so what is the r? R, which is equal to 4 pi epsilon naught n squared h cross squared by z e square m. So we can apply here z e square by 8 pi epsilon naught r, 4 pi epsilon naught n square h cross square by z e square m. Okay, the total energy value is z e square by 8 pi epsilon naught r. We already found the value of r from the radius of stationary orbits. So I am going to apply the value of r here. So z e squared by 8 pi epsilon naught, the r value is 4 pi epsilon naught n square h cross square by z e square m. So I am going to rearrange this equation. So z square e power 4 m by 32 pi square epsilon naught square n square h cross square. Okay, so this is the final equations of total energy. See here that when the n is increase, at the same time the energy also increase. Why I am telling this? Energy n, it is the principal quantum number. I already said the function is not happening a particular time, it is happening a many times. So that's why I added the principal quantum number. So that's the thing I am saying here also. Energy when it is increased, the same time n also increased, and when the outermost shell should always greater energy compared to the innermost shell. Okay, this is the Bohr formula. First we had found the stationary of the radius, and second we found the total energy of the electrons in that orbit. I am going to conclude this session with here. Thank you.